Good day, everyone. My name is Fang from Xuzhou University of Technology. I'm really honored to have this opportunity standing here to have my presentation for my paper. And you are welcome to communicate with me by email shown on the screen. First of all, my paper is named Research on Weaving Methods, Innovation and Device Development for Onboard Sensors of Logistics Vehicle, and it consists of 5 parts. In the part of research on we in motion at home and abroad, I will explain the reason for what I do this research and what we can do for industrial area. In the second part, I will show you the weighing method innovation and device development for onboard sensors of logistic vehicles. And in the third part, we will talk about the structural innovation technology. In the first part, I will show you the innovations of this research. At last, the application examples are shown. So let's start. The sensor weighing is divided into dynamic weighing and static weighing. The static weighing accuracy mainly depends on the sensor itself. The accuracy of dynamic weighing results is related to the precision of sensors and the installation and using method, working conditions, and other factors of sensors. If the improper installation or operation approaches is adopted, the impact of interference on the system is difficult to detect and estimate it in advance, and is challenging to realize error compensation through algorithm and improve measurement accuracy. The crucial problems of dynamic weighing technology is inaccurate results. The weighing error exceeds, while the average error should generally be controlled within 30%. Dynamic weighing can be divided into direct dynamic weighing and indirect dynamic weighing. Vehicle weighing is divided into weighing with the vehicle and weighing on the platform. In other words, it's ground weighing. You ready? One end of the dynamic weighing sensor is connected with the carriage, and the other end is associated with the vehicle axle. The weight of the objects acts on the onboard sensor, and then the force is transformed to the internal chips to produce microelastic deformations. The stresses and the strains can be calculated by the physical signal changes from the deformation, which are processed through the condition circuits. Thus, the weight value of the object is obtained. Due to the interference limitation caused by the connection, the dynamic weighing value is inaccurate and the error exceeds. Therefore, we get a new research idea that is described as follows. The two ends of the onboard dynamic weighing sensors should not be fixed with threads simultaneously. In principle, it can be divided into two states. One is that the carriage and the weighing object works in the vehicle transportation states. In these states, the weighing products, carriage, sensor, mounting base, and axle are connected into a piece of equipment with high rigidity to ensure safe transportation. The other is to descent in the weighing state. In this state, the car stops. The weighing devices of logistics vehicles fall without restrictions of forces outside the vehicle direction. The weight or carriage contacts with the upper end of the sensor by the spherical point in the center of wing communication. The weight is weight in a free state of being affected by gravity and support. The lower end of the sensor device is fixed to the welt with the axle through the sensor mounting base. That is to say, the pan or dish of a steel yard is specified. The wing objects and carriage are not connected with the upper end of the sensor by a thread, and there is no restriction on the upper end of the sensor to realize winging. There are two possibilities for these winging devices with poor accuracy. One is that the weight's center of gravity exceeds the wing area, and the other is the sensor have problems. To innovate and discover the use method of the onboard sensor of logistic vehicles solves the bottleneck problem of onboard wing problems in principle, because the wing time of the onboard wing devices is relatively short compared with the whole working time. The wing sensors are disconnected in the transformation states, which effectively improves the service life of the sensor wing devices. Independent wing method innovation and device design for onboard sensors of small and medium-sized logistic vehicles are studied in this paper. Also, the wing sensor protection device and control method are discussed. The principle of the onboard wing device is that the gravity of the wing object acts on the sensor body and is transferred to the internal chip of product microelastic deformation. The gravity is always vertical downward, and the microelastic deformation of the sensor chip is one-dimensional linear. According to the microelastic deformation, the stress and strain are calculated. The signal is collected, processed, amplified, and calculated. The weight value is sent to the display instrument of the vehicle terminal and then to the system management sphere through the mobile communication. The tests found that when the same weight load is applied to different parts of the car, the instrument output will display different weight values. The test results show that the sensor's installation mode, orientation, and load distribution have other effects on the measurement results. The following problems can also be found after the market research. It is found that the supporting frame of the experimental car body is not entirely rigid. The connection between the sensor and the car is rigid. During the installation of the sensor, the fixing boards will add a specific interference force to the sensor in the non-gravity direction. In principle, four sensors should be in the same plane, ideally. The flat surface should be perpendicular to the gravity direction. Limited by the installation conditions, it is difficult for the four sensors to be in the same plane after installation. The load cell structure is designed, and the technology of sticking stress-strain sensor chip is used flexibly. The winging accuracy of the onboard winging device is improved by testing and calibrating data on the prototype many times. The onboard sensor weighing device and method innovation of small and medium-sized logistic vehicles are as follows. In the small and medium-sized logistic transformation vehicle without a hydraulic transmission system, the onboard sensor weighing device is designed. The carriage and weighing objects are lowered to the weighing position, one weighing. A thread fixed connects the connecting end of the sensor and the mounting base. The other end of the sensor is in an unrestricted free state so that the weighing object could be weighed freely without any restriction. One weighing is not needed or the vehicle is in transportation. The carriage and the weighing thing raise to the vehicle transportation states. The carriage and the weighing objects are connected with the vehicle bridge through the vehicle weighing device to form a highly rigid body to ensure the vehicle transportation safety. The working principle of the onboard weighing device for medium and small logistic vehicles is shown in Figure 1 and Figure 2. When the carriage and the weighing objects are in the lower position, they can be weighed without any restrictions to realize free weighing. There is no gap between the tapered shaft and the taper hull, and the automatic alignment can be realized. The lifting thread is self-locking under the action of the vertical downward force of the weight, and the thread lifting thrust is significant when the lifting hardware is rotated. When the vehicle is in the transportation state, the tapered shaft and hull are matched without clearance, and the bolt is fastened with double safety. Innovation is found that two ends of the load cell can be connected with a screw simultaneously through scientific research. The end of the load cell base is fixed with the axle by bolts. The other end is recommended that no connection screw holes be made and two working states are used. The weighing device of the vehicle sensor is lifted to the upper position to realize safe transportation. The force on the sensor changes from pressure to tension. The carriage and weighing objects are free to contact the upper end of the sensor through the weighing contacts to realize free weighing without any restriction. In principle, the interference and rhythm factors are eliminated, and the bottleneck problem of inaccurate weighing with logistic vehicles is solved. Xuzhou Huaihai Technology Company Limited, an application and promotion enterprise of scientific and technology achievements, is engaged in the development, sales, use, and maintenance of software and hardware of onboard terminal and handheld terminal XGZS001. The technologies of vehicle networking, visualization, vehicle terminal software, Internet of Things, parking service and management fees, overloads of passengers and freight vehicles on highway, mobile communication, visualization, onboard terminal video monitor devices achieve astonishing results. From 2018 to 2020, the new increased profit is 3.29 million yuan. The new increased tax is 435,000 yuan. The foreign exchange income is 3.02 million US dollars and the total expenditure is 1.86 million yuan. In May 2018, Xuzhou Daoge Information Technology Company Limited introduces the XGHP001 system software and hardware, which was researched and developed by Xuzhou Institute of Engineering and carried out the application demonstration of scientific research achievements. In the past 3 years, it increased profits by 7.15 million yuan and taxes of 910,000 yuan. A foreign exchanges of 310 US dollars was generated and a total 3.86 million yuan was saved. Remarkable social and economic benefits have been achieved. Thank you very much for watching my presentation, and don't be hesitant to contact with me. I'll be very glad to connect with you. Thank you very much. Goodbye.